Hey everybody, my name's Dylan, and I'm just going to work through practice problem number 4 from the practice problem worksheet. Sabetta started doing it in class, and I just thought it might be helpful to run through the whole thing. So we start off with the problem here. We have the partial derivative in terms of time of n, our function n, is equal to d times the second derivative with respect to x of n minus 3 times the first derivative with respect to x of n plus some constant h times n. And our boundary conditions are going to be that n of 0 of t is n1 and n of l and t is n2. And these are inhomogeneous boundary conditions. So that makes the problem a little tougher, but we can work through it. The initial conditions is going to be like at time 0, our function n will have some function of x. Okay, cool. So now the first step, as Sabetta pointed out in class, is to let n of x and t be some steady state solution that's only a function of x, so it's not dependent on time. It's a long term solution, plus another solution that's a function of x and t, and this solves the Dirichlet boundary conditions. Which means that there's like a fixed value at the boundaries. So this is going to be our steady state. This is going to be our regular solution to the Dirichlet problem. So let's start with u of x, us of x first. Okay, and in this case we know that the time derivative, not u, n. The time derivative with respect to n, steady. Sorry, crumpled my page a bit there. Okay, is going to be 0 because there's no time dependence. So that leaves us with a simpler equation, which is the second derivative with respect to x, like this, equals 0, because now this term has gone to 0. Okay, sorry about that crumple job. Okay, cool. So now what we're going to do here is these essentially can be treated now as full derivatives. I like to think of it as full derivatives now. Now we know how to solve these, that the characteristic equation of this is going to be d times alpha squared minus 3 alpha plus h. And that's just using the ansatz of e to the alpha x. Cool. Now we can use the quadratic formula to solve for alpha here. So alpha is going to be 3 plus or minus the root of 9 minus 4dh all over 2d. Okay, great. So now we know that alpha 1 will be plus and alpha 2 will be minus. So we can then apply, since this is the one that's giving us these inhomogeneous boundary conditions, because the Dirichlet one is working with fixed boundary conditions at 0, and this is the one that's giving us these inhomogeneous boundary conditions, the long-term solution, which will end up being constant between the two boundaries. We can now apply our boundary conditions to this. So we know that n of s is going to be some constant a times e to the alpha 1 x plus another constant b e to the alpha 2 x, where alpha 1 and alpha 2 would come from this. Now applying our boundary conditions, our inhomogeneous ones, which are given here, we know that n of 0 of t is n1, so that means that ns of 0 is going to be n1, which we can see here when we plug in 0 is just a plus b. And then similarly, ns of l equals a e to the alpha 1 l plus b e to the alpha 2 l equals n2. Now these are two equations with two unknowns that we can solve for. So we're not going to go through explicitly and solve for every single part of this and solve for the A and B, but it could easily be done, and I'm sure on the exam it wouldn't be so rigorous with the algebra. Sorry, I was out of frame there. Okay, great. So that is the first part. Now let's look at the second part, which is a little more interesting, which is the Dirichlet boundary condition. So since we have that n equals ns plus n bar, we can rearrange this and solve for n bar equal to n subtract the steady state. Okay, great. So now we can look at our boundary conditions, and we're going to have, this is what Sabetta kind of ran through in class here. So n bar x of 0 is n x of 0 minus the steady of x, right? And we know from this that n bar x of 0 is a function of x because this is given as a function of x, sorry, not boundary conditions, initial condition here. And this is the steady state. And then we also have from the boundaries that Dirichlet boundaries. So this is what I was saying earlier, is that the two endpoints 0 and L are fixed at 0. Okay, cool. So we're going to use these later on, but just these are important to keep in mind. Okay, cool. So now what we're going to do is we're going to use separation of variables, our favorite technique, which will be that n bar is x as a function of x times t as a function of t. Okay, cool. So we're going to plug this back into our original equation, which I'll write up here. Again, just so we're all reminded. Cool, so that's our original equation. We're going to plug this this ansatz, I guess, the separation of variables, into that. And so we're simply going to get x times t prime equals dx prime prime times t minus 3 x prime t plus hxt. Now, as usual, we're going to divide the whole thing by x times t. This cancels nicely here, cancels, cancels, and cancels. So now we see we have two essentially ordinary differential equations that are only in terms of one variable. Minus 3x prime over x plus, and this x cancels out as well, plus h. Cool, so we're going to set this left side, and we're going to set this equal to negative lambda squared, and we're going to set this right side also equal to negative lambda squared, which are just constants, and that satisfies this equation. So that gives us first t prime over t equals negative lambda squared, and then solving for that, we know that t prime equals negative lambda squared t, so therefore t just equals some constant. In the notes they call it t naught e to the negative lambda squared t. Cool, so that was easy for our, oh gosh, I keep going out of frame here, sorry, for our function of t. Now we're just going to do the same kind of thing for our function of x, but it gets a little bit uglier. So first we're going to rearrange, we're going to set this equal. Sorry, let's start with this. It'll be easier if I show you. Plus h equals negative lambda squared. Okay, we're going to multiply through by x, and we're going to get dx double prime minus 3x prime plus hx equals negative lambda squared x. And then simply moving this over, we're going to get this equation now. Dx double prime minus 3x prime plus h plus lambda squared times x equals 0. Notice that this negative sign becomes a positive because we just moved it across the equal sign. Okay, great. So now we have this equation, and again, we can find the characteristic equation of this using an ansatz of like e to the beta x this time, let's say. That's unclear how I wrote it, sorry. So we'll say like x equals some e to the beta x. And by plugging that in, we're going to get d times beta squared minus 3 beta plus h plus lambda squared equals 0. Now again, we can just use the quadratic formula here. And so we're going to get that, so let's go over here. We're going to get that on screen. I'm trying to be on screen, okay. We're going to get that beta equals 3 plus or minus the root of 9 minus d times h plus lambda squared. And then all of this divided by 2d. And then we know from past experience that this is only going to have like non-trivial solutions to the boundary conditions when beta is imaginary. So we're going to factor out a negative 1 out of here underneath this root sign and put an I out front. So it's just going to be beta. This is just, if you're confused about this part, just look back on the solutions to like the second midterm or something, and there's a question exactly like this. I think it's number 1 on the second midterm. So now these are just going to switch places. Lambda squared minus 9, and it's all still over 2d. Okay, and then we know that when these are roots, we're then going to get a solution that looks like this. So this 2d in the solutions, actually, they don't include this 2d from the denominator, which I believe is just a typo, because this 2d should be part of this and also part of this, both terms in the root. I'll show you in a second. So our solution should then be of the form x equals e to the 3x over 2d. In the notes, they just have e to the 3x, but I'm quite positive that it should be over 2d. I actually made this mistake in the midterm, and so I'm quite positive this is right. But maybe double check with somebody before you take my 100% word for it. Okay, times a constant times sine, and inside sine should be this term here. So you're going to have the root of d times h plus lambda squared minus 9 all over 2d, and then times x. And again, in the solutions, they don't have this 2d on the denominator, but I'm again quite sure that it's part of this root, so it should be there. And then we're going to add d, some constant times cosine, the same thing, h plus lambda squared minus 9 all over 2d times x. Cool, so now this is our general equation for x. And then now we can use our boundary conditions to solve for these functions. So let's go to the next page. I'm just going to quickly rewrite this. 3x over 2d times c sine d h plus lambda squared minus 9 over 2d x plus d times cosine the root of d times h plus lambda squared minus 9 over 2d times x. Okay, great. So this is what we had before. So now we're going to quickly apply our boundary conditions. So we're given that we know that this is true by our Dirichlet boundary conditions, as I mentioned earlier. We know that these are Dirichlet. And then from this, we now know that because we defined n to be a function of n bar, sorry, to be a function of x and t, if this is 0 at these for any time, we know that this implies that x of 0 equals x of L equals 0. So now we can use these conditions to then find c and d. So first let's start with x of 0. So we know that x of 0, this sine term is going to go away. So now we're just left with this cosine term, and that has to equal 0. and also this goes to 1, and so therefore this implies that the coefficient d must equal 0. And then from x of L, we're going to have, that implies that this sine term here, c times sine of all this junk here, equals 0, and there's going to be, and sorry, this in the previous case, this cosine goes to 1 because this x is 0, so then it's just exactly d equals 0. But in this case, we're going to have an L still here. So we're going to have all this junk times L equaling 0, sine of all this junk times L equaling 0. And so we could set c to 0, but we don't want a trivial solution. So what we're going to do is we're going to set everything inside this root minus 9 over 2d times L. This x has become L, and we want this to be equal to n times pi. And now we can do that little thing when we make this lambda n, we have like a countable number, an infinitely countable number of eigenvalues to solve this problem. And so now we know that lambda n will solve this little equation we have here. And I don't want to solve it right now, and I don't think that's necessary for the exam. So we're just going to say that lambda n solves this. Okay, so now we finally get that n bar x of t is then equal to the sum, n going from 1 to infinity, of e to the lambda n squared t. So remember, this comes from this here, this solution here, and we're going to combine this t naught with this c coefficient. So then we're just going to get a coefficient, let's say a of n, and then we're going to get this x function, because we're multiplying the two. Our n bar is separation of variables, so we have e to the 3x over 2d, and just sine now because the d went away. Sorry, let me think here. Right, okay. So this should be, sorry, one sec. Yeah. Sorry guys, I forgot a factor of 4 in all these. So there should be a factor of 4 here that I was missing. Okay, great. So that's just a little, whoops. So we're going to do 4d times h plus over 2d x. Great, and then now from here, this is where it gets kind of weird, I think. We want to put essentially our equation for x, which is dx double prime minus 3x prime plus h plus lambda squared x equals 0. We want to put this in Sturm-Liouville form. And you guys should know how to do that. It kind of explains it a little bit in the solutions, and you should get a weighting function. You should get a weighting function, I believe, of e to the negative 3x. So then you can use this weighting function. And essentially what we're doing now is we're representing n bar of x and t as an infinite sum with this coefficient. And we know the value of these lambdas here, these lambda n's, but we need to know this coefficient. And using orthogonality, we can just say that this coefficient is n bar x of 0, which we know, one second, I'll explain this in 1 minute. So what this gives us is these are the eigenfunctions here, and these eigenfunctions are essentially, if we move this out of the way, it's this e term here multiplied by the sine term. Those are our eigenfunctions in this situation, and this is the function here that we're trying to represent, and we know that this, x of 0 is equal to f of x minus the steady state solution, which we found earlier. So now we know this, so therefore we can put that in for this function that we want to represent in terms of our eigenvalues, eigen functions, and then that will give us a solution for a to the n, a of n. We can then plug that in here, and then finally our solution is going to be that n is this crazy long expression for n bar x of t plus the steady state that we found earlier. And that's your final solution. Again, yeah, I guess these eigenfunctions would actually, this would go to 1 because time is 0. But anyway, this is the general idea here. I really don't think they're going to ask us anything this difficult algebra-wise on the exam, but these are the main ideas to understand. So I know this is a long video. Hopefully it helped. Maybe watch it on double speed. And again, just to clarify, all of these factors of sine here, including my roots earlier on, should have had a 4 in all of these, like it did here. So this one had a 4. I just forgot to include a 4 in these calculations. So all of these should have a 4. Sorry for that little mistake. Okay, great. Hope this video helped you guys, and good luck on the exam.